Okay. Welcome to the last lecture of this module. Here we will discuss about, well, in several variable calculus you do not stop at taking first derivative, right. You then take second derivative, then third derivative, and finally arrive, and you will finally talk about functions which has all derivatives, and then you talk about Taylor's theorem and Taylor's formula. We will do that next week for several variable, but for time being this lecture we concentrate on higher order derivatives. So, same setup, f is from U, open connected set, maybe connectedness is not essential for this lecture, Rm, and we know we can define for some x in U, we can define this derivative d f x, which is a linear map from Rn to Rm. Let me write it that this way, d f x belongs to L Rn to Rm. So, this is the set of all linear maps from Rn to Rm, and also in the, if I write it in matrix form, these are all, if I fix basis for Rn and Rm, then this will give us all m cross n matrices, real matrices. So, if you talk about second derivative, you must consider this x going to dfx, but now you see this is the map from U to, so df, if I call this map df, this is the map from U to dfx belongs to L of Rn to Rm, which is itself a vector space. If you want to now talk about the second derivative, that is d square f, so x in U, d square f at x, that is a derivative of this map. This will be a linear map from U is in Rn to L of Rn to Rm. Well, you see it is already matrix valued, these fellows are already matrix. Now, you are defining maps from Rn to matrices. So, it will be again you can say it is a matrix, huge matrix, where each entry is a matrix of order m cross n. So, total matrix will be m cross n into n. So, this is very difficult to write down, and but people still do analysis, but let us not bother too much about this thing, because writing that in a matrix form does not help much. Okay. If you want to do analysis, you have to think of some other ways, maybe we will encounter or may not, we may not in this course. But there is one thing, if we take real valued function, this becomes little easier, in the sense that suppose I have f from U in Rn to R, real valued, and you know actually to talk about differentiable function in f, you can write f as f1, f2, fm, and you understand the properties or differentiability of each component fi, and then you can talk about derivatives of f in terms of those. So, enough to, for all practical purpose, if you want to talk about higher derivative, you consider f from Rn to R, and for Rn to Rm you start from here and then go with the formula we have it earlier. But now this dfx for x in U dfx is a linear map from Rn to R. So, this is a row vector which we have actually written as, actually it is, we have fixed notation grad f at x, which is we know del f del x1 del f del x2 so on del f del xn. This is the reserved notation for grad. So, you see now x going to grad f at x, this is now a map from u which is in Rn to Rn again. So, d2 of f x, maybe we will write it as a special notation. I do not want to use this notation because this is reserved for something else. Okay, let me still write for this course, I am not going to talk about this. This will be in a linear map from Rn to Rn, and this I can write it as m cross n matrix. How? Well, grad fx is from u to Rn, grad f, so it is a vector in Rn. Now, I will consider this is a function. So, what I will do? I will write grad f at x as, it is a Rn to Rn, del f is map from Rn to Rn. So, I can write it as n components, right. We have done it before, where each fi is grad f del xi. Now, I know what is the second derivative of this map. This is, we have already known that this will be del fi. So, this will be del f1 del x1 del f2 del x1 so on del fn del x1 del f1 f2 del del f1 del fx2 del f2 del x2 so on del fn del x2 del f1 del xn so on del fn del xn. We know this from before because I have written actually the Jacobian of this map del f. So, this is Jacobian of this map del f at x, correct. But now, I know what is fi. So, this matrix will be, I can write it is, okay, I do not have place to write here, maybe I go back to that board. So, let me keep the setup. So, grad square f at x is, now I write what is definitions of fi. f1 is grad f del x1. So, del square f del x1 del x1 del x1 square del f f2 is del f del x2. So, that is del x1 del x2 so on del f del x1 del xn, next del f del x1 del x2 del square del square f del x2 square so on del square f del x2 del xn del square f del x1 del xn so on del square f del xn square. which is written as del fi, sorry, del f del x j x I. I equal to 1 to n, j equal to 1 to n. And some books use a special notation for this, and we will use it also in our next calculation next time. It is called h f at x and written as Hessian of f at x. Okay. So, if you do not remember which way to follow del x j del x I, always go back to this way, that you write del f x is equal to f 1 f 2 f n, f I equal to then this thing, and then apply the derivative formula. There is nothing much to remember here. So, you can always in 1 minute you can just write it down, but if you know the how to write derivative of a map from R n to R n by component wise. Now, this matrix has this property, you see 1 2 entry is del x 2 del x 1 and 2 1 entry is del x 1 del x 2. So, order is changed. So, what I can see from here that this matrix H is a symmetric matrix if del square f del x j x I equal to del square f del x I del x j for all I j. So, if the mixed partial derivative, they are called mixed partial derivative, there are two different components involved. If the changing the order they are equal, then the matrix becomes symmetric, but this is not always the case. For example, I give you a very elementary example. Let us say f from entire R 2 to R, f of x y equal to x into y x square minus y square divided by x square plus y square, when x and y both not equal to is not equal to 0, it is not origin, and 0 at the origin. What you can calculate here, so do this calculation yourself, that del f del x, this is equal to you just calculate it, del f del x equal to, well, let us calculate it, it does not matter, del f del x, let us calculate it at 0 y, this will be equal to minus y. So, del square f del y del x at 0 0, so you verify this calculation, is equal to minus 1, whereas del f del y at x 0, this will be x. So, del square f del x del y, this will be equal to 1, clearly these two are not equal. So, del square f del y del x and del square f del x del y at 0 0, they are not equal, one is minus 1, is 1. You do this calculation very easy, you just go do the derivatives. But this is not a very likely, very nice situation for us to go ahead with the calculation, to go ahead with calculus. We want the mixed partial derivative equal, so that I get this matrix symmetric. It becomes very handy when you next time you talk about Taylor's theorem, and also when you talk about maxima and minima of real valued function, to come up with certain criteria of check maxima minima, the symmetricness is essential, otherwise it gets is a total mess. So, we actually want condition for equality of mixed partial derivative. So, we want condition such that del f del xi del f del xj and del square f del xj del xi for given ij. Let me state it as a theorem. I state it for f from u, or I stated more general Rn to Rm. U is open connected set, but open is enough here, open. Condition says, so let us fix a point. I want to always check it at a point. Suppose given I and j, given I from I in 1 to n, 1 to m, and j in 1 to n, del f del xi del f del xj both exist on a ball around delta, that is for all point in the ball around delta for some delta. See, when x naught is in u is open, there will be always a ball, but I want a ball such that this del f xi and del f xj both exist on the entire ball, not only at x naught, on the entire ball for some delta greater than 0, and both differentiable at x naught. That is this del phi del xj both differentiable at x naught. Then del square f del xj xi equal to del square f del xi xj. So, mixed partial derivative are equal. So, what is the condition? They must be, of course, these two must exist. So, they must be differentiable at x naught, but the condition is they are both exist, I missed, most important, and continuous. But why I did not write? Because I am saying there is a differentiable, but differentiable at x naught means it is already continuous at x naught, but I want it continuous on the entire b x naught delta. But if anyways, so you can have this or may not have this, okay. Continuity at x naught is enough, but it has to exist on the entire ball, that is important. So, you add and continuous or not, it does not make any difference, that is what I make. Okay. The proof is little long, and the proof is not going to be, we are not going to use the entire idea of the proof anywhere, but still you need a proof once you write a statement. So, what I write here is proof, but I here write a sketchy proof. So, I give you the entire idea of the proof, you complete the lines in between. Okay. So, to do the sketching, you go like this. First, make your reduction that I am only concerned about two, xi given xi and xj. So, let us only consider, because nothing going to change for Rm and Rm, f from u in R2, because two variables are involved, and R. For Rm what you do apply component wise and two variables are involved. So, R 2 is enough. If I have R m, you do component wise. Okay. And without loss of generality, your x naught is 0 0. This is just to make the calculation easy, because u is any set in R 2, here is your origin, but you can always shift the origin in such a way that 0 0 belongs here, right. That is not, there is a transformation on origin, and that does not change any property, differentiability, continuity, anything. So, we choose, we are going to go add the hypothesis. So, some h greater than 0 such that h 0 cross 0 h, this set is in U. So, here is my U, some U around origin. I choose a h such that this square of length h and height h, this is completely in U. With that, what you do, for a fixed h, define g of x equal to f of x h minus f of x 0. Okay. Then you apply mean value theorem to get this is equal to h into g prime at some z 1, right, z 1 in 0 to h. But immediately you can write g prime z 1 equal to del f del x 1 at some at z 1 h minus del f del x 1 f at z 1 0. I am applying the definition of what is del x 1, then x and y only. Okay, fine. That was my second step. So, you verify all those steps. I am not writing the entire proof. Third step is you again write del f del x at z h as applying MVT del square del x square at 0 0 at z, not applying the condition of the derivative, sorry, applying this is differentiable del f del x 8 del f del x at x 0 z 0 as del square f del x square 0 0 at z plus h into del square f del y del x 0 0 plus mod z h into the error term u 1 h, where u 1 h will go to 0 as h goes to 0, because h goes to 0, z is also goes to 0, z is between 0 and h. Okay, from that what you do, you calculate g h minus g 0, it will come out to be del square f del, okay. So, let me skip this step because this needs some technicalities. What I actually one can show that this divided by h square, this goes to del square f by del y del x at 0 0. And what you do in the next step, you repeat the entire thing by defining g 1 y equal to f of h y minus f of 0 y. So, here I take x h x 0. So, I do with x and I do g 1 g 2 and you again show by the same step g 1 h minus g 1 0 divided by h square, it will just ulta, just be other way round, sorry, this goes to 0, this thing as h goes to 0, this as h goes to 0, and final observation is g h minus g 0 equal to g 1 h minus g 1 0. So, these two limits will be equal because numerators are equal, denominators are h square. So, that is the idea of the proof, you fill it up the detail. Thank you.